Hello and welcome back to Historical Geology. Today I want to do Chapter 14, Mesozoic Earth History. And the key thing that's going on during the Mesozoic is the breakup of Pangaea. And it really starts in the late Triassic and into the early Jurassic, around 185, 180 million years ago. And we see that it's first going to break up between the Africa part of Gondwana and Laurentia, which is North America. And we start to form the Atlantic Ocean. And we know this because of these magnetic anomalies, right? We're seeing the magnetic stripes on the seafloor developing at the mid-oceanic ridge, in this case the newly formed mid-Atlantic ridge, and it gives us information as to when different parts of Pangaea were rifting. So looking at the modern seafloor here, these are the different colors that refer to the ages. So the blues, the dark blues, are Triassic, Jurassic, about 180 million years old, and these greens are maybe Cretaceous, and then we're getting into the Neogene, or Paleogene and Neogene here with these reds and yellows. And so just looking at the Atlantic Ocean, because that opened up when we rifted Pangaea, you see that it must have first rifted between Laurentia and the Gondwana part here, Africa, because that's where we see the oldest seafloor, this late Triassic, early Jurassic seafloor here, about 180 million years old. The South America, Africa part of Gondwana didn't really rift till Cretaceous, really the early Cretaceous part here, because here we don't see any of these Jurassic anomalies or of magnetic striping down here. So that's one important thing that we're seeing. The other big thing that's happening is we have an all-encompassing ocean called Panthalassa. We'll say more about that in a moment. When we get to the Cretaceous, we have this Cretaceous interior seaway, and you can see much of the Cretaceous world here is covered by epiric seas. And so what could be causing these epiric seas during this last period of the Mesozoic era? So there's worldwide transgressions to the breakup of Pangaea. And so we have high heat flow along mid-oceanic ridges. So that just means that along these mid-oceanic ridges, they're going to be huge. They're pushing up from so much heat, and so they make the volume of the ocean smaller. They decrease the volume, which means they're going to push oceans up onto continents, right? Because the water has to go someplace. So if you're pushing from underneath, this water is displaced, in this case, onto continents, and we get this Cretaceous interior seaways. So it's highest since Ordovician. About 1/3 of the present land during this time was covered under these epicontinental or epiric seas. Then I have this idea of calcite versus aragonite seas. So let's look at the document camera here. So aragonite and calcite are both carbonates, right? And they're polymorph because they're both composed of calcium carbonate, except they have a different physical chemical structure. One thing about calcium and magnesium are similar in size, and calcium and magnesium can fit into the calcite structure, but they have a little bit but magnesium cannot fit very well into the aragonite structure, right? So it can fit into calcite but not into aragonite. And so during calcite seas, these are times when we have low magnesium to calcium ratios. Whereas for aragonite seas, when we precipitate aragonites, they're going to have high magnesium to calcium ratios. So how does this happen? So it has to deal with these mid-oceanic ridges. So today, both aragonite and high magnesium calcite precipitate from seawater. So we talked about these oolitic limestones, these ooids that form by rolling on the seafloor, usually warm tropical waters, like in the Bahama Banks. And so we see that during, like today, and also during the earliest part of the Cambrian, in the late Paleozoic and this early Mesozoic time, we're seeing these aragonite and high magnesium ooids form on the seafloor, high magnesium calcites here. But during late Cambrian and Ordovician and really getting into this Cretaceous time, we start seeing calcite deposit. What's causing these magnesium-calcium fluctuations? So it's a change in the volume of the mid-oceanic ridge, MOR for mid-oceanic ridge. So if we increase seafloor spreading, we're going to make these ridges larger. We're going to get more quickly hydrothermal circulation. We're going to increase the length of these mid-oceanic ridges. So this circulating seawater at the mid-oceanic ridges, these hydrothermal vents, we're going to transfer calcium from rocks to the seawater. And we're going to extract magnesium from seawater to produce greenstone, chlorite, and epidote. So basically these is kind of a hydration alteration of basalt. So we alter that basalt into these green minerals. That's what makes it green stone. So it's a meta basalt there. More seafloor spreading and bigger mid-oceanic ridges, right? We're going to lower the magnesium to calcium ratios, right? Because we're going to circulate more. We're going to transfer more calcium from the rocks to the seawater, and we're going to extract more magnesium from seawater. So we decrease the magnesium, increase the calcium, we get calcite seas. So smaller ocean volume, right? We get those epyric seas, we get those marine transgressions. So we're seeing that in the Cretaceous period as an important time. When we see periods of low mid-oceanic ridge activity, so the seafloor mid-oceanic ridges kind of subside, the volume of the ocean basin gets bigger, so oceans, water goes back into the ocean basins. And because we're now not extracting as much magnesium from seawater because we're slowing the rate of hydrothermal circulation, we're going to have higher magnesium to calcium ratios, right? Larger ocean volumes, we get those marine regressions, right? That's when we get these aragonite seas. So here we're going to increase our reservoir of magnesium because we're not taking as much out, and we're not really transferring very much calcium from mid-ocean ridge to the seawater, right? So we increase our calcium-magnesium ratios. On this figure here, we're seeing the geologic time on the bottom, Paleozoic, Mesozoic, Cenozoic, going all the way here to the Neogene Quaternary. We're seeing a graph that shows the magnesium to calcium ratios, and we're seeing an increasing rate of ocean crust production. So in other words, the higher these numbers are, the faster ridges are growing and moving. So obviously these higher values here, we're going to have lower magnesium calcium ratio. So you can see here we had very fast seafloor spreading with the breakup of Pangaea, so we have low magnesium to calcium ratios. And when we do have that, we're going to have calcite seas. When we have low production of mid-oceanic ridges, low seafloor spreading rates, low rates of hydrothermal circulation, we're going to have less magnesium being extracted from seawater, and which means we're going to be having higher ratios of magnesium to calcium. And so that's going to give us our aragonite seas. So you can see we had a little bit of that going on here in the early Cambrian. We had it again going on in the Permian through the Triassic here. And then again, we're seeing it today. And then remember, we talked about the modern corals. Today, they're the scleractinians. And you could see that they were starting to develop and become the more abundant coral species here in the Triassic and the Jurassic. Then they decreased in the Cretaceous because of having more calcite. You'll see that later on, especially when we talk about the Gulf Coast of North America, we develop rudist reefs. And the rudists are really these bivalves. So they're not even corals. They're like a clam that makes a colonial, very porous colony. And then as we go along here, seafloor spreading decreases here, calcium magnesium ratios increase again, and we go back to aragonite seas. We start making the coralline algae, which also likes the aragonite and the high magnesium calcium, and we're back to the modern corals developing over here. Other things that are happening too is note that as we have more magnesium in seawater, we're going to be able to make more of this magnesium sulfate. And these are evaporites. Magnesium sulfate is the mineral gypsum. When seafloor spreading is more abundant and we're seeing more calcium, less magnesium, so we see these low magnesium to calcium ratios, you can see calcium and potassium follow each other closely. So we see potassium chloride, which is a mineral called sylvite. So we get these potassium chloride evaporites developing here. So again, during most of the Paleozoic here, and then into the Cretaceous, and a little bit into the Paleogene here. But today we're back to the magnesium sulfate, the gypsum forming. We talked about the magnetic anomalies. We talked about how Pangaea, especially the North America, Africa part, started rifting 200 to 180 million years ago, Triassic period. Really by early Jurassic, it had opened up and you started forming the Atlantic. We start seeing overflow from the Tethys Ocean, the Pacific Ocean, and the Southern Ocean that's going to come in to start forming this Atlantic Ocean. And we see these evaporites, lots of these evaporite deposits that we see during this time. And it's also telling us that where the Atlantic Ocean was opening was tropical latitudes where we're seeing this evaporation. So during the Jurassic period, we have a wide Tethys Ocean between Europe and Africa. as Laurentia and Africa, Eurasia and Africa spread, that Tethys Ocean expands toward the west. Also, during the Jurassic, Antarctica, Australia, India, they're still attached, right? Because we're not going to really start rifting these until the Cretaceous time. But then by Cretaceous time, Pangaea is really breaking up. We see the Cretaceous Interior Seaway. The Tethys Ocean now is an equatorial seaway, and we see waters from the Pacific, Atlantic, Indian Ocean, and they're all mixing. With equatorial waters free to mix. Africa and South America are wide apart. Finally, Australia and Antarctica separate, and India begins to move north, and it's near the equator. Eventually, at around 50, during this Eocene time, it's going to collide with Asia to form the Himalaya range. So another thing that's going on, we got these climates that are changing as Pangaea breaks up. So remember, the end of the Permian, Pangaea extends from pole to pole. It's a supercontinent. And we talked about Panthalassa, the all-encompassing ocean, and it stretched for over 300 degrees. And so each degree is about 60 nautical miles. So we got about 18,000 nautical miles. Remember, nautical mile is a little bit more than a statuette mile. So that equates to about 20,714 statuette miles, what we're more used to. So if you were to fly in an airplane, so airplanes cruise around 550 miles per hour. If you were to fly across the Panthalassa Ocean during this time, it would take you nearly 40 hours on an airplane to fly that distance. That's how big this ocean was. It's pretty amazing. So we mentioned how much of Pangaea was arid, deserts, and that's because these continental interiors are far from where the moisture is, the ocean. So that moisture has to travel a long distance, and what's more, it has to go over mountain ranges. And so there's this concept called the orographic effect. You've probably heard of the rain shadow. So as these clouds move, the moist clouds move over, they have to rise and elevate above these mountain ranges. When air rises, it expands, it cools. That expansion causes the air to lose hold of its moisture, so you see precipitation, and then that is going to lead to a forest or greener climates on the windward side. But on the leeward side, we see it's going to be more arid. That's where we see our rain shadow. So if we have multiple mountains, we're going to get arid and then even more arid and more arid. So eventually the interior of Pangaea becomes desert and dry. We also look at these climate-sensitive deposits. When we see evaporites, we know we're arid and dry, like gypsum or sylvite. Red beds, sand dunes, they can occur just about in any environment, but usually when we see large deposits of these, we're looking at arid environments where we're seeing winds. If we have coal needs humid, whether it's tropical or cold like peat bogs. The other thing your book mentions about is this idea about temperature gradients. So it just means that the steeper the gradient between poles and equators. So if the poles are really cold and the equator is very warm, you're going to get quick turnaround, faster, because it's a steep gradient. But if the poles and the equator are about the same temperature or close to the same temperature, then the circulation is going to be slower, right? So these temperature gradients affect how ocean and atmospheric currents circulate on our planet. So the greater the difference, the faster the circulation. So remember, albedo is the reflectivity of material. So oceans have a pretty low albedo. They absorb about 90% of solar radiation. Continents have a little bit higher albedo. They're only absorbing about 30% solar radiation. Snow has a very high albedo, so it's less than 90% of solar radiation that's absorbing. So snow can reflect a lot of sunlight. So during the time of Panthalassa, temperature gradients were not that steep. We had a pretty much warm ocean from the poles to the equator. So this is the time of Panthalassa. So you can see there's ocean current circulation here, and it's relatively slow. Once we started breaking up Pangaea and North America and Eurasia started moving to higher latitudes, getting colder temperatures up here, displacing some of that ocean up here, the currents start getting more complex and faster.